question. The presentation is the sensor technology for greenhouse robots. This time, the sensor technology is including the some prediction for greenhouse robot is one sensor based on the sound signal, and another kind of sensor is based on the fluorescence imaging, which is quite different with the normal imaging system we use in agriculture. So the first topic is about the progress in development of agricultural robots in Japan. Let's skip some because we need to catch the time. In the past, especially in the past 15 years, the population of the Japanese farmers decreased half, which Japan faces very serious labor shortage. So there has a demand for the agricultural robots. We summarize this is the top 10 fruits and vegetables that cultivated in a greenhouse. Them like spinach and onion has been mechanically harvested, but other fruits and vegetables need to be harvested by some robots because robots need to judge based on the maturity level. So first robots, one typical robot I'd like to introduce is about the tomato harvesting robots. Our lab developed the first harvesting robot of a tomato about 40 years ago. At that time, we used the camera and the arm effector to realize the harvesting. And recent years, there also has many university research about the tomato harvesting robots. And this is one robot developed by the Panasonic company. They are trying to apply this robot for the cherry tomato harvesting. Because the cherry tomato in one cluster, the maturity level of the different fruits, different tomato is different. So this kind of robot need to judge the maturity level and harvest one by one. It's the size of this tomato is about 3 to 4 centimeters. So and due to the maturity level difference, so the robot is necessary. In our lab, we also developed the strawberry harvesting robot. We focus on the strawberry because the harvest for the manipulator is quite simple. That doesn't have much obstacles. And another very important reason is the fruit, especially strawberry in Japan is very expensive. So that has affordable equipment and investment for the farmers. Many years ago, we did some questionnaire about to the farmers about their demand for the harvesting robot of strawberry. We know the market entrance for the sector reached about 60%. After that, there has been maybe 4 generations of the strawberry harvesting robot has been developed. The first generation is designed for the harvesting robots. The strawberry is cultivated on the tabletop and it's harvested from bottom to top. The second generation is for the strawberry that cultivated as the hill. This strawberry will be gathered at the center of the cultivation bed, so the robot can just harvest from top to the bottom. These two kind of harvesting robots reach very high success rate, but the problem is that its effector is the suction method. So to harvest one mature strawberry, the nearby immature strawberry will be harvested. So this is one disadvantage of this two kind of robot. So from the third generation, we think about to recognize the maturity level of the strawberry and harvest one by one. So that has this kind of robot. It has an effector and it has one camera at the top, and it can recognize the position of the strawberry, and there also has cameras on the index factor to recognize the peduncle for the harvesting. So after this robot, we think how to commercialize robots. So we collaborate with companies. The Shibuya Seiki company is a very big company in Japan about the greenhouse robots. We realized that when harvesting robots that for the mobile bench, this kind of robot system that the density of the strawberry is quite high, much higher, is about 2 to 2.5 times that compared with the conventional planting method. In this kind of cultivation way, is the robot is very essential because human cannot work beside the inside the ridge. So we think about this robot will be welcomed for the market, but this robot has been sold on market about 7 years, but that has many problems of this robot, so it's not so welcomed for the farmers. One bigger problem is that the robot is designed for harvesting all the strawberry in a greenhouse. That means the robot should be big enough to have much capacity. So it should have a big storage area. This robot normally has very big and heavy, and it moves very slowly. So the overall cost of strawberry is about $50 US, $50,000 US. But Japan its government has some financial support for this kind of robots in the greenhouse, maybe 50%. But it's still a high cost for the farmers, so not so welcome for the market. This is another typical harvesting robot developed by a company. The company developed this for harvesting the green pepper. So this kind of robot is only designed for like harvest like maybe 20 or 30 peppers. And it can storage in a tree of the robot, and later when it crosses somewhere, it can put this pepper in a big tree, and farmers can come and take this harvest these peppers. The cost, the first stage of the initial cost of the robot is quite low. It's about $1,000 US. Why it's so cheap is the company, they will charge the farmers based on the yield, like 10% of the yield. So the companies, they want to make it cheaper and acceptable for the farmers. So we summarize some trend of the harvesting robots. One big trend is that there has recent years new technology like AI and IoT, and some new sensors like RGB camera and the SLAM method for navigation. And another trend, the important trend is that one robot is designed for harvest multiple targets, not only one fruits, maybe also other like a cucumber or eggplant, many fruits. And the robots during harvest, after harvesting, the robot is also able to grade based on the quality of the fruits or vegetables. Because the robots also has sensors, and some robots has a light source, so it's possible to realize some sensing for the environment and plants. So for this recent trend, that has especially for the new operating model and the multi-functionalities, the new sensors are necessary. So here comes our research topic. First topic is about the navigation system. Why we need that? Because we summarize the development of the agriculture robots. In the past 40 years, there has many robots has been researched and commercialized, but harvesting robot is still ongoing. So how about the next generation of the robots? We think the next generation of the robots is the robot size should be smaller, that multiple robots can work together in a greenhouse. Another important trend is that we can see the agriculture is become more and more precision. So we think about is it possible to give very precise treatment for single plants? So this may be another possible trend in the next generation of the agricultural robots. So luckily we get the fund and we are trying to realize such a topic that we want to get the multiple robots in greenhouse and realize the single plant treatment. With the agriculture, the robot system, we think possible for the next generation that it has multiple robots. For example, that has 2 or 3 harvesting robots and also has some like a quadcopter and also some robot for the sensing of the environment. This kind of robot system, it has a higher efficiency and less weight and lower cost. To realize such a system, we need a conditioning system to get the path of the robot. The environment we think about is because the typical greenhouse in Japan is about 15 meter by 10 meters. So we think to develop such a conditioning system to get the multiple robots in such an environment. This is as we know, the GPS plus agriculture robot has been well researched and developed. Especially in recent years, there has many about like rice planting robots, and this is released maybe 15 years ago. But this video is quite new. It's about 5 years ago. The robotic companies, they are now selling this kind of robot, and welcome to the farmers. Its commercialization is very success. But how about the greenhouse? The GPS cannot work in the greenhouse because of the signal dumping and the reflection. So we think about it. That has some other alternative system in greenhouse. One possible method. Also, many researchers research about the slab, and also UWB is UWB is the most common indoor navigation system. But we think about to develop a new system, it has a relatively higher accuracy. The accuracy, we think it should reach like 20 millimeter, like 2 centimeter. And actually we did that. We did previous system, we realized.
妈妈，这个声音好像还没办法。
Okay. Previously we realized 30 meter by 30 meter area with 2 centimeter accuracy. And the cost is relatively low. It's just US dollars, maybe less than, it is less than 800 US dollars. And also very, yeah, it's just a 200 gram. So we think this system can be improved and possible for our new proposal. This is now the available system on the market. One is very famous in Marble Land. This another is in Chinese, a Chinese company. And this is the Japanese company System Watt. We collaborated with the company that developed this sensor, but this sensor is developed 10 years ago, more than 10 years ago, like 15 years ago. So we now think about to update this system. So how does this system work? This system, first we need to make the sound signal. Sound signal is the is the way we generate this system. Use M sequence signal with a camera wave. To get this, we call it the spread spectrum sound signal, SS sound signal. The speaker will emit the sound signal. At the same time, the microphone will record all the signal. This is received signal and this is the emitted signal. So we let these 2 signal match. As these 2 signal match, then we will have a very high peak. This high peak is the available time of the sound signal. So this calculation is named cross correlation calculation. So by this method, we can estimate the available time of the sound signal. So we can know the time from the speaker to microphone, and we can also estimate the velocity. So we can know the distance from speaker to microphone. So at least we know 3 distance from between the different speaker and to microphone. Microphone is mounted on the robot. At least we know 3 distance, so we can get 1 position of the robot. So by this method, yeah, we can estimate actually this method is quite similar to GPS and also similar to UWB based interpretation system. So that has some sub-objectives in this research topic. The first is about near-far program. Near-far problem is very common. This means if we, the robot, for example, robot is near to this speaker, and we want to measure this distance, but this distance is quite far from this speaker too, but from speaker one, but the signal reached to the microphone all at the same time. But that has the interference. For example, this noise is too strong, so it's noise for this speaker. So we think about how to solve this problem. The first solution is to use FDMA signal that the false speaker emits some signal at a different frequency. So by this method, this is one solution. Another solution is the TDMA signal that make it simple is the speaker emits some signal at a different time. For example, the first 0.25 seconds, only one speaker work, and the following 0.25 seconds, another speaker work. This is all the speaker work at different time. So this for this two kind of signal, there is no noise interference or sound interference. So we did some experiment in the greenhouse, and here is the result. We just emphasize the accuracy. We compare the FDMA signal and TDMA signal, and the accuracy is about the TDMA has the best, the accuracy about 2 centimeter, and for the FDMA, the accuracy about 5 centimeters. The difference is located at the modulation method, because one for the TDMA signal, the bandwidth of the correlation peak is different. So there has some this kind of product, but just a very small difference. Another second objective is about noise interference, because you may ask about how about the noise tolerance against the noise. We build the noise model of the agriculture robot in the greenhouse. The most noisy robot is a quadcopter, because the quadcopter has a wideband noise. It's not like the motor noise maybe end at 10 kilohertz, but for the quadcopter, its noise is quite high. It can reach 50 kilohertz. So we did some evaluation to test our system performance against the noise of quadcopter, and here is the results. There will have some interference. It's not so big, so we can say the system has some noise tolerance. But we say the some noise tolerance is because if the sound source is far to the receiver, but the receiver is mounted on the robot, on the quadcopter. So there has some limited range. Limited range in this experiment is about 15 meters. But this signal can be improved. We can select some other signal with better noise tolerance, but it's possible to improve the noise tolerance. The third research topic is about the we want to realize the orientation into mission. So we developed two methods. One method is that we put two microphones on the robot. We can know, because the one microphone stands for one XYZ coordinates. So if we have two microphones, two coordinates, the vector between of these two microphones is the orientation of the robot. Another method is based on the time difference. We proposed another method. Actually, the second method is summarized from some reference, and the real experiment results show the second method has a better performance. The overall performance of the orientation measurement is about 1.6 degree. It's a good performance. It's high. It can be applied for the quadcopter and on the robot. The research topic is about Doppler shift, because the sound signal speed is about 300 and sound speed is about 340 meters per second. But if the robot is moving, that means that we have this reference signal. But problem is this reference signal is constant, but the received signal, it has Doppler shift. So the wavelength will be changed. if the double shift happened, these two signals are very difficult to match. So it leads to the low noise tolerance, and the system cannot detect the arrival time. So we proposed some new algorithm based on extracting the carrier wave, because all the signal is we know the carrier wave of the signal. So if we can extract the carrier wave, we can estimate the velocity, and we can estimate how much Doppler shift happened, and we can do some computation. For this experiment, we need a wireless system. So we developed this sensor. The first part is the wireless receiver unit. It will be put on the robot like this one. It has two microphones and some sensors. We will FPGA will record it and record all the signal and put and send to JET for processing. And we also have the sound emitting unit, because this emitting unit will be set. It will be fixed in the environment. All the speaker position will be measured by the total station, so we can know the position of the speaker very accurately. And this is the two system, and we put it first. We put it on the ground robot, and we also put it on the quadcopter to test the performance of our wireless system. So here is the result. The experiment is we didn't do the experiment in the greenhouse is because our system work at 4 Hz. That means that 1 second the position will be measured 4 times. And we also have AMU. AMU update frequency is 100 Hz, because we are also trying to make our system update the frequency to be 100 Hz. So that means the normal monitoring system cannot work. So we use a Zichen motion capture system. Motion capture system is covered is set in this area, and it can provide 0.1 millimeter accuracy with 100 Hz update frequency. And here is the video. We control this robot. This is the output result. The blue point is measured by the Zichen. It's ground truth. The red point is measured by our system. And we try to let the environment mimic to the greenhouse environment, that with similar sound reflection index. Actually, for this, the experiment in this video, the sound reflection index is much higher than the greenhouse environment. And here you can see this is the area of the two microphone. Two microphone means two coordinates, and here is the orientation area. This research we focus on the basic performance of the sensor. So we didn't try other sensor fusion method to minimize the error of the sound-based appreciation system. Actually, we have some simulation. We also trying to apply the IMU for this system with the sensor fusion. So, okay, so here is the results. The result shows dynamic 2D error is about 5 centimeter, and static is about 4 centimeter. And the important thing is this research focus, this experiment focus on the Doppler shift compensation. Without compensation, the fail detection rate is about 70%. But with this compensation, the fail detection rate is only 2.6%. That means in 1,000 times the measurements, there only has 26 points that failed. As you can see, the failed measurement is at this kind of point. Okay, so the conclusion is that we develop a passive conditioning system for the multiple robots in a greenhouse, and we did some subjective. The first is about near-field problem. We solved the and by two solutions, one is the TDMA and another is FDMA signals. For the noise tolerance, we build the noise model and did the experiment with the quadcopter noise. And for the orientation, here is the result. The Doppler shift compensation, we reach very good performance at compensate the signal with the Doppler shift. And so the next is about this one. This is about the fluorescence imaging. When we think about you to research about this, because fluorescence imaging is a very interesting topic. As you know, the most, for example, the most harvesting robot, all the harvesting robot has a camera and most has some light source. But if we change this light source into UV, that means we can capture fluorescence imaging. So fluorescence imaging is very easy to be captured by this greenhouse robot, but it has many functions. So the first we research about the green pepper. The first topic we start about very basic performance, very basic that characteristics of the green pepper in the fluorescence that we totally measured maybe 14 cultivars with different color. You may know the sweet pepper has different color, like green. This we see is the purple, it's dark, very dark, and yellow and red. But in fluorescence imaging, all the fruits fluorescent blue color. So this is very interesting because if you use some machine vision system, you use deep learning to recognize the green pepper for harvesting robots or monitoring, you need a very big data, but it has different color. So your database is very big. But if we use the fluorescence imaging, all the images can be sent into one database because all the fruits, all the sweet pepper fluorescent blue color. And we summarize its characteristics in macro and micro scale. Second topic is during experiment, we found something interesting. As you see, this is the green pepper image captured under white LED. But this is under UV LED. We use the UV LED to capture the fluorescence imaging. But we can see there has some, this dot is invisible under the white LED, but visible under the UV LED. It's very interesting. It's like some, we see it's like a fingerprint for the green pepper. It's very unique because all the green pepper, it has this unique pattern. So this research summarized talked about the reason of this fluorescence features. And the third topic, based on this result, we did some matching algorithm because we treat it like a fingerprint. So when we do this kind of tracing for the single pepper, is because in greenhouse there has a very big database nowadays, very precise information. But this information is associated with in Japan, there are many breeding facilities. The breeding facility will also get many information about the quality information, and consumers also can provide some feedback. But all this information, there is no information flow between them. So we want to build some tracing method to, for example, give feedback to give the feedback from a breeding facility to the farmers, and make this kind of information flow to connect this data flow. So how we do that? We capture the image, both color and fluorescence in the greenhouse. This is the greenhouse image, and this is the post-harvest image. And we recognize this, we do some image processing to recognize this fluorescence feature and do some matching. This is the greenhouse image. This is the post-harvest image. You can see if there has some match points, we can do this kind of match. So we realize that it's like a fingerprint for the green pepper. We can do this kind of traceability, and the success rate is quite good. It's about 83% success rate. So we realize this kind of traceability. So now we are also collaborate with the company to try to apply this in some robots in greenhouse. This is just all this, most of it in post-harvest stage. For another topic, this topic is about the agriculture products quality inspection technology. The fruits and vegetables in Japan is quite expensive, as you can see. For example, I focus on the strawberry research. This strawberry this almost 1 kilogram is about $70 US maybe. So it's pretty expensive, but so the consumer very care about the quality of the fruits. The conventional method, if there is no breeding facility, the farmers harvest all the fruits and vegetables with different grade and send to the retailers, and the market will give some price and they sell to the consumer. But the consumer, if the consumer has purchased the low quality fruits, it's very helpful to the reputation of the retailer and the farmers. So in Japan, most fruits and vegetables, most fruits will be sent to the grading facility, and based on the quality, they will the grading facility they will pay to the farmers, and the consumers can purchase the quality as they want. This is the video we commercialized in our lab based on some technology in our lab. This is a citrus. This is send all the package of the citrus to the sensor line. As you can see, conventional method is only visible and IR, but we applied fluorescence and also some AI technology. Why fluorescence is work well? Because and fluorescence its advantage is the real-time night study and low cost. So how it works? The method is first, we use some light source. We use some filter to only keep the excitation wavelengths. Normally, we use UV light for excitation. This is an example of olive oil. If this UV light reach olive oil, the fluorescence it happened, so it will change the red color. This red color is the chlorophyll, and we use some filter to filter the UV light, and this red light, emission light can be observed by the human. We see it's very cheap. It's because this example I captured, this is the citrus. This captured using my smartphone, just my smartphone, and with a UV torch. The total cost is maybe $10 US because it's just the cost of the UV torch. It's very cheap. So you can see under the white LED, there is no abnormal there, but here there has some surface damage. Why the surface damage happened is because farmer, when they have this citrus, they will use scissors, but it will hurt. It will generate surface damage to the fruits sometimes. And another reason is that during package, during transportation, the peduncle of the citrus will hurt the nearby citrus, so it generates this kind of surface damage. But it's very difficult to detect by other sensors, but very effective for the fluorescence. This is we can classify many this kind of surface damage, which is invisible, the UV under the visible light. We think this system can also be applied for the greenhouse robot. It's because just use the greenhouse robot is a camera, and we just add a UV LED. UV LED is very cheap. It's by this combination, the conventional harvesting robots, after harvesting, it can recognize the quality of the fruits. if there has some abnormal fruits or low quality fruits, it can do this kind of sensing. So when harvesting robot, it can be multifunction. It can not only harvesting, it can also do some grading. Another example of the fluorescence research in our lab we commercialized is about to detect the quality of the fish, because in Japan the raw fish is very welcome to the market. As you can see, I took this kind of image. This is the fish meat. We cannot see some abnormal there, but under UV light we can see this is anisakis. It's a kind of worms in the fish, but invisible under white light. But we can use UV light to generate a fluorescence for this kind of detection. This is also commercialized. My research topic is about strawberry. So why I think how I start this research, because I purchased this strawberry market. This one package is about 15 strawberries, but the cost is about $8 US. It's very expensive compared with China, but when I take it home, I realized there has one strawberry with mold. This strawberry has a very short shelf life. So I'm considering, is it possible to do some classification at early stage? For example, the harvest robot harvests this strawberry and immediately do some grading to pick out this strawberry. Is it possible? From conventional research, there has they point out the strawberry has a much fluorescence compound and possible to be some index which is related to the strawberry shelf life. So I did experiments, prepare the three kind of samples, healthy and on-sheet and overripe. On-sheet means because this strawberry, during cultivation of strawberry, the farmers will use some sheet to protect strawberry from the field. On this kind of sheet, the surface is very wet, humidity is very high, and strawberry is very sensitive to the humidity. So we prepared this kind of sample and we did some measurements, and here is the result. We found we storage the strawberry about 7 days. During 7 days, that has totally 7 strawberries that is out of shelf. It's very low firmness. But we also measured the fluorescence spectroscopy. It's a fluorescence characteristic. We know that some strawberries that we see is strawberry with short shelf life. This kind of strawberry that has some blue fluorescence. So we use this blue fluorescence as index. Here is the imaging result of one cultivar named Sakahonoka. This is image is under white LED. This is UV under UV LED fluorescence imaging. This is captured about 1 hour after harvest, but this is after 1 week storage. You can see this color difference is not so big, but this become dark. But we can see fluorescence imaging, the whitish increased much. So, this sample with a very short shelf life, but it's possible to be classified using the images after harvesting. Just within 1 day, within 1 hour after harvest, we can take this image and do some grading. This is another cultivar. Its fluorescence imaging is more obvious that after storage, the blue fluorescence intensity became stronger. But on D0, we can do some classification. So we only use the D0 image for some as an index for classification. This example, why I select this example? Because we randomly harvest this strawberry in greenhouse, but at day 4, this strawberry has mold. we can see from D0 the fluorescence intensity is already very high, but with storage, yeah, its intensity increasing all the time. So we use only this D0 image as an index, do some classification, and this explains why what happened. This is because the surface there is fluorescence is intensity increased for this short shelf life sample. And here is with some this classification. This grading is very simple. Just use HSV class space. We didn't use other complex statistics method. We propose a area ratio which is based on this thresholding. It detects the whitish area that has the blue fluorescence. It can effectively classify the 7 strawberries that with a very short shelf life, we see is soon spoiled strawberry. And this we also build a model for this data. We only use the day0 data that within 2 hours after harvest, which this method can be applied for the harvesting robot and other sensing robot in the greenhouse. And this is about during storage. We do some model and we can do some prediction of the quality change during storage. Okay, here is the result. We try to realize this kind of robotic system. For this system, the first important thing is to use some position sensor position system to get the path of the robot to do some position and navigation. Our target area is about 50 meter by 10 meter, and we reach the 10 centimeter level accuracy for this robot. And we also develop some fluorescence imaging system, which is very low cost and most important, the low cost, and it can reach many functions that the normal white LED that cannot reach. We did the plant phenotyping for the for the 3 peppers, and do the classification of the strawberries that is very easily to apply this sensor for all these sensors are very easy to be applied for the greenhouse robots, for example, the harvesting robot. And here is some interesting image I'd like to share. This is eggplant captured by just using my smartphone and UV LED. So the smartphone is camera can realize such a function. This is a very low quality eggplant. This is very fresh. This freshness is not so high. And this is for the green pepper. We can detect some abnormal samples from outputs. Yeah. So that's all for my presentation. If you have any questions, we have some time for discussion.